welcome to Don Labs. This episode we're going to talk about Ohm's Law. It's the most important formula in electronics, and getting used to it will help you in almost every future project. So the easiest way to remember how to use and rearrange Ohm's Law is in a triangle like this. So I'm just going to draw a triangle on the page, and it has a V, an I and an R. Okay, now the V represents voltage, that is measured in volts. The R represents resistance, and that is measured in ohms, and the symbol for ohms is the Greek letter omega, which is like an upside down horseshoe with two little bits on the end. And the I represents current, which is measured in amps. Now if you're wondering why the current is an I and not the same letter like the V and the R is to voltage and resistance, is because C, the letter C, is actually used for the speed of light. So when they devised this system, current was given the letter I. Now the easiest way to rearrange this formula without having to learn any sort of complicated algebra or even knowing how to rearrange a formula, really easy, just put an equal sign in front of the value you want to find in the triangle. So we start off with the V. I'm going to draw three triangles. The first one we're going to find V, so we put V equals, so write that here, V equals I times R, because they're next to each other. In a formula, when they're next to each other, you multiply. I, R. Voltage equals current times resistance. Okay. Second triangle, we're going to put the equals in front of the R. So we have resistance equals V, voltage, over the I, voltage, divided by current. And our third triangle, you guessed it, we're going to solve for I. So we put the equals there, and we have I equals voltage V over the R, resistance, voltage divided by resistance. So that's all you need to do to rearrange. Just put the equal sign in front, and whatever's written in that triangle, that is the way the formula is written. V equals IR, R equals V over I equals V over R. It's as easy as that. We're going to draw a simple circuit before we then go ahead and put it on the breadboard. I've got some components here. We're going to use a resistor, an LED, a power source on our breadboard, and that is it for now. So let's just move this out of the way. I'll draw a simple circuit. We're going to have a power supply. It's going to be a 6 volt power supply. Excuse the drawing. We're going to have a resistor at the top of our circuit. We're going to come down into an LED, and we're going to come back out the LED, back into the power source. So we're going to put a voltmeter across the resistor, and when you measure voltage, the meter that you measure with goes across the component that you want to measure, and we're going to put a voltmeter across our LED so that we can measure the voltage here and here. Now in a series circuit, all of the voltage adds together, and the total is the voltage of your power supply. So the circuit that we're going to be building, the LED happens to be a white LED with a forward voltage of 2.85 volts. So we already know this value. This is going to be 2.85 volts. And that means that the power supply minus this voltage here has to equal this voltage here, because that's all that's left after this has been taken out of this. So the voltage across our resistor is actually going to be 3.15 volts. Now what that means is we can use this, one of these formulas, to calculate some values. Now we need two values to get the third, and in this circuit I want to limit the current because the LED can only handle a certain amount of current, and this circuit I want to limit it to 10 milliamps. A milliamp is a thousandth of an amp, or 1 amp divided by 1,000. So you have to be careful when you're writing these formulas. Current is in amps in Ohm's law. So if you're using milliamps, which you might be on a lot of smaller circuits, especially logic circuits, then you want to write the milliamps as amps. Okay, so I want 10 milliamps, which is 0.01 amp. Okay, now I know the current that I want, I know the voltage that I have across this resistor, and I want to find out what value of resistor I should use. So I need to use the formula that's down here. So I need to use R equals 3.15, because we already have our voltage here, divided by the current, which is 10 milliamps, there. Now if you do 3.15 divided by 0.01 in your calculator, okay, you are going to get a value of 315 ohms. So that is the resistor we need to use if we want 10 milliamps. Now I haven't got a 315 ohm resistor because it's a little bit of an oddball size. I'm going to use a 330 ohm resistor, okay, which is this one right here. So with 330 ohms, I'm going to put 330 back into the formula just to make sure that the current hasn't changed too much from what I want. So I know the resistance and I know the voltage, because I know I have a 330 ohm resistor and I know I have this voltage here still. So if I know the voltage and I know the resistance and I want to find the current, I use this one down here, I equals VR. So I do I equals 3.15 divided by 330, get 9.5 milliamps. Or if you was to write that as amps, it would be 0.0095. We're going to build the circuit on the breadboard. So we're going to build it exactly like it is here. We're going to get the multimeter into shot and we're going to test these values just to see if they work in the real world. Okay, you're going to get tiny bit of variation because the breadboard's not exactly a perfect test bed for doing circuits. It's literally just prototyping, but we'll see. Okay, so we've got a positive supply on the breadboard. I'm going to bring that up with a jumper cable, and then from the positive supply we're going to go into our resistor, which is our 330 ohm resistor, which is just there. From the resistor I'm going to put another small wire, which represents this wire here, just to space it out a little bit. You don't have to do that on the breadboard, but I'm going to space it a bit so it makes it easier for us to see the meter. Then I'm going to go into the anode, which is the positive end of the LED, which is the long leg of the LED, and the short leg of the LED, which is the cathode, which is the negative leg. I'm going to take our jumper cable and I'm going to go from the negative up to negative of the breadboard. Okay, in fact I am going to swap these wires to make it easier for you to remember which end is going into the negative and which end is going into the positive. There we go, that's a bit better. Then I'm going to take our power supply, positive, and negative, and we have a lit LED. From our negative end of the LED, I'm going to place the negative end of the meter, And then on the other end of the LED, I'm going to attach this end of the meter, and we'll get a reading just to verify that it is the forward voltage that I originally said. 2.85 volts, exactly what we thought it was. Now if I take that off the LED and do a reading basically from here, the positive end of the breadboard is the same as measuring from here because they're both connected. So if we put our meter here, we'll get a total voltage. Our total voltage in the system is 6 volts. And if I take that off this end and I just put this across the resistor, so we have what we have in the picture here, the voltmeter across the resistor, we should get a 3.15. Yeah, 3.15 volts. Okay, so the voltages are all correct. So now we know that the voltages that we used in our equations are right. We're going to test to see if the current is correct through this resistor. Now we've predicted the current through this resistor should be 9.5 milliamps. So next step, so we have positive coming out into the meter, through the test equipment, out of the meter, back into the other end where the positive would have attached to. Okay, LED's lit, circuit is made, and we are getting 9.13 milliamps. Now we've concluded that it's all working the way it should do. What happens if you had this exact same circuit but someone had used a 220 ohm resistor and you wanted to know how much current is that 220 ohm resistor allowing through the circuit? First thing I'm going to do is just recheck the LED, just make sure we're getting the same forward voltage. So our forward voltage is 2.92 across the LED this time, so it's a little bit different. Total voltage in the circuit is still 6 volts. We're just going to measure the voltage across the resistor. 3.07 volts. So that is the value we're going to use. We have a voltage. We have the resistance. We know this resistor is a 220 ohm resistor. And we want to find the current. So we use this one. Again, I equals V over R. So I equals 3. I'll use the current multimeter value, 07 divided by 220. I equals 0.014 amps. milliamps. If you notice, I use a small m for milli, because if you use a big M, that's mega, which is a completely different scale. I've got 14 milliamps with a 220 ohm resistor. What if I wanted to keep that resistor but change the current? Let's say we want our 10 milliamps back again. So now we need to know the voltage, so we use V equals IR. And if we plug these values back in again, we want V equals 0.01, that's our 10 milliamps, times 220 ohms equals 2.2 volts. So we need 2.2 volts across this resistor here. We know the whole system is 6 volts, and we know this LED is 2.85 volts. So if you want 2.2 volts here and 2.85 volts there, then we know that when we add them together we get a value of 5.05 volts. So we need to reduce our supply from what we've calculated, that if I plug the supply voltage back into the breadboard, that our resistor should have a value of 2.2 volts. Let's check that. 2.14. That's pretty close. Like I said, you're going to get a tiny bit of variation. 1 because the breadboard, 2 because of the leads that we're using. And we're going to swap the multimeter over to current, and we are looking for 10 milliamps. Here we go. 9.3, so it is slightly off. Okay, so we're off by 0.7 milliamps, so 0.7 of a thousandth of an amp. Now, hand in hand with Ohm's law is the power equation, and you can also use the triangle for this as well, just to make it a bit easier for you. So the power equation is P equals IV, or you can also write it as P equals I squared R, but I prefer P equals IV because we can put this in our triangle. So we're going to draw a triangle, P equals IV, and then we can do exactly the same as what we've done with the Ohm's law triangle, and then if we put an equals here, we have the P equals I times V. If we put an equals here, we have the V equals P over I. And if we put an equals here, we have I equals P over V. Now P is power, it's measured in watts, and the same with that goes for watts that goes for the amps. You have to be careful with milliwatts because smaller logic circuits are going to be using milliwatts. Now when we were resisting the current, so that's the flow of the circuit with the resistor, you're taking current away from the circuit. That current has to go somewhere. Energy can't just disappear, it has to turn into another form. So that energy is being dissipated through that resistor as heat. So you have to be careful with the power, because if you dissipate too much power through the resistor, it's going to go poof, it's going to explode, it's going to set on fire, it's going to melt, and your circuit could become dangerous. Okay, so using this, what we're going to do is we're going to take our original circuit with our 330 ohms, and we're going to measure how much power was actually going through that resistor. So our power is equal to current times voltage. Okay, so in our original circuit, the power is going to be equal to, we're going to take our 9.5 milliamps and we're going to express that as amps. So we're going to do P equals 0.0095. Okay, that's 9.5 milliamps times, and our voltage, if we go back to our original, what you'll remember was 3.15 volts. And we get a power which is equal to 0.0299. So when we convert this into milliwatts. Move the decimal place. Rounded up, it's 30 milliwatts. So we're getting 30 milliwatts dissipated of heat through this resistor. This sort of size resistor is 1/4 of a watt, which is 250 milliwatts. So that is well within tolerance. But if we went a little bit higher on our circuit with the power, then we'd have to use something a bit more beefy, like I said, to stop it melting. So if, for example, we had 10 volts across a 10 ohm resistor, using the triangle we have the voltage and the resistance. So we go back to our triangle on this page, we want the current. So it's I equals V over R. I equals 10 over 10. Therefore, I equals 1 amp, which is a substantial amount. Now we go back to our power equations, and power equals current times voltage. So power equals 1 amp times 10 volts. So power equals 10 watts. Now if you was to put this through this resistor, it would melt. You would have to use something more like this, which is a 10 watt 10 ohm resistor. Okay, so just be mindful when you are building and testing these circuits to not only check your Ohm's Law triangle, check the power triangle as well, just to make sure you're not pumping too much heat dissipation or too much power through your resistor, and avoid melting. Even with this 10 watt 10 ohm resistor, it can withstand 10 watts, but if we put 10 watts through that, it would be very, very hot. So this concludes our episode on Ohm's Law. Have a little practice, messing around with a few values, and try it on paper, test it on your breadboard with your multimeter. Just be mindful of the power that you're putting through the resistors, like I said. Hopefully this will give you a better insight into making your future breadboard circuits. Thanks for watching, don't forget to like and subscribe, and don't blow up.